Oh, thanks, Bruno. And thanks for coming to this talk. Is everything on now as far as you're getting? Okay. Bruno mentioned sparse distributed memory, and the idea there, really the inspiring idea was what happens in very high dimensional spaces. Very high dimensional spaces are something for which we don't have much intuition. Our 3 dimensions don't really prepare us for the. So we have to tease out the properties by just mathematics and analogies. And so I would say that's very much what is in that book, and also in the work that I've done since then. And as you can see in here, it's just high dimensional appears in my title, and randomness is another thing which very nicely goes together. This time I'm interested in brain in terms of what does it say about the mind, or actually, how do you implement the mind in the brain? And implement is sort of a funny word in here. What kinds of things suggested by the architecture of the brain could, if we model them mathematically, could give some properties that we associate with mind? And what do I mean by mind? Well, one thing is that mind deals with concepts, and here are some such concepts. You could take any word in the dictionary, almost any word. I don't know if and or are concepts, but any nouns and verbs and adjectives. And so you get concepts like man, woman, country, red hot, truth. All of those, comfort, transcendence, reciprocity. All those are concepts. And if we believe sort of that the brain is sort of the physical underpinnings, then all of these have to have some sort of physical realization in the brain. And if you say like some concepts, I'm just taking how we intuitively feel about concepts. Some concepts are closer to each other. Man is sort of close to a woman, the concept of a man, whereas man and a lake, they are concepts. Well, you can't see that they really anything in common with them. But the interesting thing is, in our minds, we can bridge any 2 concepts with only a very small number of intermediaries. Like from a man, I said man and lake are not related, but man is related to fisherman. Fisherman is the fish, and fish is the lake. And other connection, man is the plumber. Sort of, they feel that they are close concepts. Plumber is sort of somehow could bring out water, and water. So there are various ways of connecting concepts with only a very small number of intermediary concepts. And this is one of the things that a very high dimensional space would give you the property to, the license to expect. If concepts are somehow represented as points of a high dimensional space, then although you have 2 concepts very far from each other in some sense, in what sense we'll soon see that, then they can be very distant from each other, but there's something in between that is very close to both, and that is one of the things that our intuitions about 3-dimensional space don't make us expect. Another thing, concepts are related in other ways, like and you probably have seen these kinds of comparisons. This is to that, and then there's intelligence. This 5 is to 10 as 15 is to what? Well, I've given 2 answers to that, and so you can see that there are various ways how concepts can be related. Man is the woman, like son is the daughter. If I had blanked the daughter, I think most of us would have sent daughter instead of aunt or some other. Yeah. Then here's another one. It's interesting. Man is the woman, as country is the language. How would you get that? We talk of fatherland. We talk of mother tongue. So they have all kinds of interesting relations that concepts have, and somehow if we believe in it, that mind has physical basis. Somehow we should be able to model those kinds of things in our modeling. So we need some physical representation for these things. And how do we model? We try to find some significant correlations between some items of interest and then some mathematical system. And why mathematical? The thing is that once we get into some mathematical systems, then there's a lot of machinery in mathematics developed that lets us then see what else might be true. If we anchor, I mean, if we say this corresponds to that in the mathematical system, then we can go in the mathematical system something else that this mathematics predicts, and then we can look at if that's also true in, like in this case, and that it would work that way with concept as well. And the mathematical system that I'm talking about here is a very high dimensional space. And when I say high, it's like the dimensionality is over 1,000. And I've taken to use the word hyperdimensional space. If you are in physics and talk of hyperspace, 4 dimensions already hyperspace. But my hyperspace is more than 1,000 dimensions. 10,000 is the number that I like to use these days. In a book I use 1,000, but in my older age I've become more daring, and now it's 10,000. And the concepts in this case would be then vectors or points of the space, or patterns. I will use interchangeably words a vector, a point of space, pattern, and there may be something else that I use interchangeably. I hope it doesn't confuse you. And we should have something like this, that if the vectors are similar, somehow then the meanings, if the vectors correspond to concept, then similar meanings would somehow be reflected by having similar vectors. And of course, dissimilar meanings, and the vectors would be dissimilar. I mean, otherwise, if everything is all are similar, then that's not interesting. And so now we come to some of the properties of these high-dimensional spaces. And the interesting thing here again to note is that the dimensionality is the important thing, and the nature of the dimensions is less important. So I use in my examples almost always binary. When things work with binary, why make it complicated? I mean, some of these examples could also be done with real vectors or complex vectors, complex meaning that the vector components are complex numbers. And I'm sure there are other kinds of mathematical objects, tensors, matrices, all those things that also could be used. But I use the simplest possible and see how far we can get it, because I feel that the important thing really is the dimensionality. And mathematically, a binary 10,000 bit binary number is corners of a unit cube, and so it's a hypercube. And so there are 2 to 10,000 such points or patterns or vectors or corners. In this binary space, Hamming distance is a nice way of measuring distance between points, a number of places at which 2-bit patterns or binary patterns differ. That's the Hamming distance. Probably very familiar concept. If there's something sort of vague, I use a concept that really needs explanation, please let me know. I'm assuming a sort of binary Hamming distance are fairly well known. There's an interesting thing when if you think of an ordinary cube, if you start from any corner of the cube and turn the rest of the cube looks identical. Same thing in 10,000 dimensional space. There's a symmetry. All points in that space, all of those 2 to 10,000 points, they are alike in the sense that if you take the point and then start measuring distances to all the rest of the points in the space, you always get the same distribution. And that means that the space is concentrated nowhere. I mean, if you take any point that everything looks like, then there can be no points of condensation. However, it looks as if the volume of space or the mass or the distances are very highly concentrated. And that again is another thing that's very important and interesting fact about about these high-dimensional spaces. Okay, so from every corner in a cube, in a 10,000 dimensional cube, you can go into 10,000 different directions, and so there are 10,000 nearest neighbors, and 10,000 choose two neighbors that are 2 steps away, 10 and k steps away, measured in Hamming distance. And if you think that every one of these points has equal probability, in other words, that they are sort of chosen randomly, then you're dealing with the binomial distribution. The distances are distributed according to the binomial distribution. The binomial has a mean of 5,000, and the standard deviation is 50, and this kind of binomial is very nicely approximated with the normal distribution. So if you want to compute sort of probabilities of this kind of binomial, I think most computers will give an overflow if you take 10,000, choose 5,000, but the normal distribution you can get excellent approximation for the binomial distribution. Now here I've tried to picture somehow a little bit of how the space is concentrated. What does it mean that you have this, the previous one that there was, back, that you have a mean of 5,000 and standard deviation of 50. In other words, we're talking of the apparent condensation. So if we take a distance, we start from any point and we start going, look, this is 1 bit apart, 2 bit apart, 5,000 bits apart, 10,000 bits apart. We just look at measure distance to all the rest of the point. Then you have to go pretty far, from 0 to 4,700 bits. And by that time you have only covered, let's see now, that's 1,000, a billionth of the space. So you have to go very far before you sort of get much of the space included at all. And then in this very narrow section, almost all the space appears, and then you can go and there's a symmetric part. If you take the cube and take 2 opposing corners, then there's here you are halfway into the cube, and then there's the opposite side that is just the perfect duplicate of this side, and that's why you get these two sort of very long tails that have very small probability. Very few points that are. There are very few points that are this close, and very few points that are further than that, and almost all the space. And that is, I think, that is probably the most significant, simple thing to remember about these spaces, that they are concentrated quite far in this midsection. So all of these, we can think of them as being similar. If you take this point and then take points that are up to this distance, they are similar or they are correlated. And in terms of distance, you cover 0.47 of the distance. Then there's a small belt that covers 0.06 of the total span, and those would be, I would say, they are dissimilar, uncorrelated, approximately orthogonal, and then they're the opposites. So that's the nice peculiar thing that the very large distance covers very small volume of the space. And so you could think of it this way: the pattern that has 47% in error. You have this 10,000 bit pattern, zeros and ones equals likely. You have 47 bit errors, so 47% errors. It is still similar to the original vector, because most points are further than that away, and so it can be identified with the original vector. This is where I think error, like our error tolerance or tolerance for variation in the stimulus, it could be explained by something like this. Is there a question there?
I'm not quite getting what you mean by volume.
the number of points of space, volume of space. You have a total space is 2 to 10,000 points, and that's a total volume of space or the total mass. And so I refer to volume as the proportion of all the points in the space. So this volume relative to 1 means that only this very small fraction of all the possible points, all the possible 10,000 bit vectors is this close in Hamming distance. That's what I mean by volume. Volume, mass, number of points. You could think of volume as a shorthand for number of points of the total space. So most vectors in this space, they are orthogonal or nearly orthogonal, and the robustness and noise tolerance comes from the fact of this very peculiar distribution of the space. Now, in this last example, I used 10,000 bit vectors that have zeros and ones with equal probability. Now I look at slightly different ones that are very sparse vectors. And what happens here? What is my sparse vector? Sparse binary vector. It still has 10,000 bits, but out of those 10,000, only 20 are ones, and the rest are zeros. In the previous case, when you have 50-50 chance, then approximately 5,000 are ones and 5,000 are zeros. So now instead of 5,000, you have only 20 ones, and then the rest are zeros. Now the number of such points in this particular space, the number of points is about 2 to 204 or 10 to 61. That's still quite a large space. And so now how is this distance distributed in this case? Now, since I make this sort of rather rigid assumption that every vector has exactly 20 ones and 9,980 zeros, then the Hamming distance between two such vectors can be 0 if they don't zeros don't overlap. If they match exactly, if they disagree in one place, then the Hamming distance is 2. So you have possible Hamming distances are 0, 2, 4, 6, 8, 10. So it's just the peculiar things that you don't get any points that are odd number of bits apart. That's I could just
21. So if there's a bit emission somewhere,
it has to go somewhere. It has to go somewhere. It's just the fact that each of the vectors is exactly 20 bits, and so if I have a little bit of overlap, so there's one extra here and one extra here. If I have a little bit less overlap, now that's why I have these funny numbers. Only the even numbers. So now, okay, 0 means that there's no overlap. The two vectors, the 20 bits in the two vectors don't touch at all. So no, they all touch. Oh, sorry, by chance that they all touch, or that they differ in one, and so you have to go all the way to 32, and still the total volume of space is so that's 1,000 million. So it's sort of whatever it comes. So it's a little bit more than billionth, but anyway, it's a very small fraction of space is closer than 32 bits. Then here at 34, let's see now. The last one here, 96% of the space is such that they don't touch at all, and that they touch a little bit, then you get this covers that much, this covers that much, and so what we're saying is this plus that should become 1. That's a total space. So here again, there's a very long distance where the number of points in the space would be within that distance. The number is very small, and it is so this concentration far away is again noticed. So these are similar or correlated, and then these would be the most of the space, most of the points, they are dissimilar, uncorrelated, nearly orthogonal. Now we talk about intermediary points between any two uncorrelated points. Between, you take that and then one in the mass. You can find points that that is, relatively speaking, close to each. Let's see if I go. So two of those that are 40 apart, and if there's some points are 20 apart, and so they are 20 away from that and 20 away from that. So something that is 20 bits away from it is considered to be very close, because it's a very, such a thing is very rare. So that is a very nice of explaining the possibility that between any two unrelated concepts you can find concept that is closely related to both, and closely means that by chance you would not get that close. And here is my example again. The man is sort of somehow close. The representation of man, the mental representation, a vector for man, would be somewhat quite close to fisherman, would be close to fish, would be close to lake. But men and lake are far from each other. Also, the intermediate points like plumber and fish, they would be far away from each other. And now when I say far away, I mean a thing like, how I feel about those. I just don't feel that plumber and fish really are close concepts. That's, if you agree with me, then our concept spaces are somewhat similar. That's I guess that would be that question. Now, how are word meanings expressed in computers? If you have done any computing and computational linguistics, artificial intelligence, programming, they are represented as nodes in a semantic net, or lists of attributes, or pointers to a list of attributes. I mean, if you do symbolic programming, Lisp and things like that, Lisp is all pointers. And so those pointers somehow represent meanings in Lisp. But all of this, in some sense, is ad hoc. It is, they are by ad hoc means they are our inventions. That's how we think we could represent them. But are they natural in any other sense? That's questionable. And they are not easy to compute with. You have to. The programmer has to do all the work. Be clever. How do you trace through lists of attributes and decide whether some two concepts are similar or not? So those are how we now represent things in computers. There are probably others, but those came to mind. And we would like to have representations such that they are derived automatically. Somehow, of course, the brain's representations are done automatically. Not all necessarily. Some things we actually learn by explanation and by looking in books and dictionaries and all those things. But a lot of it's automatic. We just grow in an environment and we hear words and pick up words, and next thing you know we're using them, and nobody ever gave us a definition. And this goes through our lives. If you have had the experience of learning a second language, you probably you probably start by going to dictionary, and that is sort of going through dictionary is something like this. But eventually you just have heard a certain word in certain context often enough, you just start using it, and you never even thought of, you know, you never thought of what it meant in terms of, you never translated into your original language. And then they should be, the representation would be such that they would be easy to compute with. Well, I'm not saying that I have answers to all those things, but I would look for the answers in something like high-dimensional representation. There are some ideas that we'll not have time to go through this time, but there's a lot of interesting work been done in this area, and I will introduce some of the basic work. In these cases, meanings are the points of some metric space. I mean, if you compare meanings, one of the desired things is they are easy to compute with. And maybe if the meanings are points of some metric space, then the properties of the metric space give you somehow the hints of how you would compute with these meanings. And such a distance is related to meaning. Close in distance means similar. Meanings are similar. Far in distance, dissimilar. This all is sort of intuitive justification for trying to represent meaning in a metric. Metric space means that it has between any 2 points of the space, between any 2 representations, we can say that have some notion of distance. 2 representations are close to each other, or they are far from each other. And so now we would like to get to the point where we derive meaning automatically from context. This is how we learn much of our own language, for example, or when we learn a second language after we are immersed in it, we start learning meanings just by exposure and the context in which the words occur. So words with the same or similar meaning appear in similar contexts together with the same words, and so they can be substituted for each other. And so the bus and train have similar meanings, say similar words, and you can see you can substitute. You can go by bus if you'd rather not drive. You can go by train, and if we have a lot of data of that kind, we eventually start getting pairings. That's where we have lots of words and lots of context, and we can that way sort of compute vectors what would capture some of this meaning in this fashion that I've talked about. One of the terms that is used for such vectors, context vectors, another is semantic vectors. And again, so I'll use the words context vector and semantic vector interchangeably. And so I will go through an example of how this has been done, and actually 2 examples of how it has been done. The material that we have used, it's been 10 million words of high school level text, and it's divided into short segments. They call them text samples, and each of these there are 37,600 of these little pieces of text on these various subjects: science, home economics, health, industrial arts. And if you get into this literature, then these are called documents. And if you go into search, like Google search, and you work at Google, then probably they also use a document for if you put a little search put a web page, that could be a document. So document just means it is some piece of text on one topic. News items in the newspaper would be documents. And so here we have this large number of documents, each on the average of 166 words, and a total vocabulary in this corpus, in this text mass, is 54,000 words, and I put words in quotes because there are such words as H2O. Any string of letters and numbers that is separated by space is considered a word, and that's how you get rather large vocabularies. And the next one is just an example of what this data looks like. Here's one of the documents. It looks like it is in science. So each one of these, you have to ignore punctuation. You have to ignore capital and lowercase distinction. So numbers will be thrown away.
Oh.
Numbers will be thrown away, but H2O is a word, and CO2 is a word.
Letters like D.
I is a word. So D is a word also. I mean, it doesn't know. How would it know? I mean, if you want to accept I, and who wouldn't, then it has to accept. Yeah. So this is pre-processed somewhat. So that you will. This is like lowercase in, and the commas disappear, and that's the lowercase a, as is that. So, and then there are some other things that linguists have taught us to do, and like words that are very frequent, like THD, the. They just very frequent words get thrown away because they just don't add anything to this particular way of doing things.
Well, in theory, though, you could leave them in because they really do no harm, right?
If your algorithm is done right, then the algorithm should wash out. But if your algorithm is a little bit dumb, then those very, very high frequency words, then they just have extra weight there. And so you're right, and that's how. And we use dumb enough algorithms that they don't. I mean, the algorithm should be sensitive to frequencies. Ours aren't that sensitive. In the example that I'm talking about, they aren't. And we now, the linguists, computational linguists talk of the models that I'm talking about. They talk of them as back-of-word models. Back-of-words means that all of this, if you rearrange the words in this document, in other words, you take each of those words, put in the bag, and mix them, and then put them again. They don't make any sense, but it would still be the same set of words. So this document is considered only as the particular set of words in that document. Yeah, you have a question?
So you introduced context as being the interchangeability.
The context is a document.
Okay.
In this case,
the two words are found together and
in the same bag, exactly. Yeah.
Whether they were next to each other in the bag or far apart.
No,
Could have been
in the examples that I'm talking about, it doesn't make any difference. In some other experiments that we've done and some research has been published, it does make a difference. So yeah.
Could you imagine that if you had two words that were synonymous,
yeah,
then in a bag it would choose one or the other, even though
of course if the synonymous words are in that, then they will both be in your tallying, and I'll show you soon how they are tallied and where they end up. But I mean, there's a lot of linguistics that we could go to in here, and I'm not justifying this on basis of linguistics. I'm just representing this as a. But anyway, this gives you an idea of what sorts of things are called documents. And so the word used document, since we have 37,600 documents, we have 54,000 words, 37,600 documents. They are first collected into a frequency matrix, and here I have sort of. Here are all the words that ever appear in this, and they are. This is the number of words. So each word has a line in this table, and each document has a column and a document that I had up there just previously. It was the document number 1728, and it had the word crystal once. It had crystals no times. I mean, this is so dumb that it doesn't even make a distinction between singular and plural. Fluid had two occurrences of fluid. Fluids, two occurrences. Fluid twice. Whereas document 1 didn't have any of those. Document D didn't have any of those. It had other words. And so we have this huge matrix of frequencies. F is of frequency, and so each entry in that matrix tells how many times a particular word appears in a particular document. And you can see, you can then count on the margins that overall crystals occurred in a total corpus. In the crystals occurred 182 times. Crystals, the plural form, occurred that many times. Liquid occurred 1,283 times. And a document 1728 that was just up there a moment ago, it had altogether 101 words. So that's our data. And so take a good mental picture of that, because we will be referring to this, if not in bodily, but at least in mentally, when I explained random indexing.
These documents have like an encyclopedia or textbook or something?
I think this was from high school level texts, but they did one of them they did encyclopedia, but we couldn't. The publisher did not let us use that encyclopedia data. I mean, publishers, they think they're losing something if they let you put the encyclopedia into a computer and then start scanning words. So I guess one of the original experiments, not by us but by another group, was done using.
What's the 5,100,000 in the corner? That's not 3,700 times the other. So that's the sum of the total number of words.
That would be the total number of words in the total vocabulary. And see, all the frequent words have been the D and of, and all those have been thrown away.
Okay.
That's why we started with 10,000, but because the very frequent words were thrown out, and I think also strings that occur only once and twice, I think they were also thrown out. If you have like string of 8 A's. It was some story just represented the sound with a long string of A's. But since that string appeared only once in a total text, it was thrown away. So this is a total number of words altogether, and in a whole corpus, and it's a total number of different words. Okay, so now I said before that you want vectors for words such that if words have a similar meaning, they would somehow be similar. They would, and it turns out that each word in the vocabulary now is represented by a vector. It's represented by 37,600 dimensional vector, and the vector has small counts in it. So we have each one of those is now a vector representing the context of that word, and I call those raw semantic vectors. So each row is a semantic vector, and it already has the property that similar if they have similar meanings, they appear. For the vectors to be similar, they have to appear often in the same document. And then if they appear in the same documents, apparently they talk of the same thing, and that's how we get this idea that you have similar meanings become represented by similar vectors. And there's several ways of measuring the similarity of vectors, like the rows. You should dot product, you can look at cosine, correlation. Any of those have been used, all give about the same results. And now how do we then test further how good our vectors are? And this is, I thought this is sort of a clever thing that they did here. They used a synonym test. And synonym test is something that is given to foreign students who apply to U.S. universities. It's known as a test of English as a foreign language. And if you're a foreign student, you have to take it and you have to pass it before they consider you are ready to study in a university. And so here's an example of what kinds of questions this synonym test involves. Okay, here. 3 questions. There are 80 questions altogether in this test, and here are example of 3. And so you would have 80 altogether go into the hallway and outside this building if you line it up like this. Okay, there's a word and then 4 alternatives. And it says, which of the 4 alternatives is most like the test word? And so you know, prominent, patterned, ancient, mysterious, conspicuous. No, so you go through this test and you mark D and you zenith and decline on it. You put B and all. So this is what the foreign students have done. I guess I did it once. I forget, but anyway, I must have passed it. And so the foreign students are rated. And now, how do you do the same kind of test with these vectors? Now, we already saw this huge matrix, and each line is a vector for a word. And now you can compare them, and so you just compare the vector for prominent for each of the 4 vectors for those, and then you pick up which of those 4 is closest to that, and that's your computed answer. And then you do the same thing. You do the same thing 80 times, and so that way your computer chooses out of those 80, makes its 80 choices. And of course, since there are 4 choices, and if you do by random chance, then you have to be at least more than 25% correct to be better than random. And it turns out that the tests at some of these things they test about as well as some of the students at Haag accepted in the universities. In other words, this kind of computed vector is able to decide which of these 4 alternatives is closest to zenith, which is these 4. Often enough that it would fit into a university, you know.
Did you look and confirm that all of the words in the test were in your corpus?
I think we had one that wasn't.
Out of both the queries
80,
and
yes.
And the 4 choices?
Yes. There's a little bit of massaging done. We did truncate, and because it meant that long words were truncated. And that way, if a long word appeared both in singular and plural, now it became one word because you dropped it. But this is all in good faith and honest. So that if you have enough, if you go through enough text, you know, I mean, Google is putting out, or whatever, web is putting out text. You have enough text to get all the words in all of these things many times over, and then you could actually have exact words. Okay, so that's how these things, these semantic vectors, automatically generated semantic vectors, have been tested. And yeah.
So I can see how this would work for the similar words.
Mm-hmm.
Could you do something like this to find antonyms of words?
Yeah. I think. Okay, this doesn't get into it. This way of doing it, but I think you should be able to do it because our brains do it. That's a sort of a cop-out answer, but it's not a total cop-out. There has to be a mathematical system. We may not have found it yet, but there has to be a mathematical system that somehow is able to capture that
presumably is getting these similarities be
Yeah.
correlations.
Yeah.
Correlations, and there must exist anti-correlations in the data set too. So
Yeah.
But
it seems like
you imagine that it would pick the antonym of man
Yeah.
would be like, or something that has just absolutely nothing to do with it, right? That would be the least correlated word.
No, those are
Yeah.
just zeros. Those just don't match.
Oh, that's true.
Yeah, and then in the first space I introduced, there actually is a space, and then there's a midsection that is sort of unrelated, and then there's the opposite. Whether that's the answer, I doubt that that's the answer. But what I'm saying is that different kind of mathematical spaces give you different possibilities of representing things, and so that's I think that the challenge is sort of finding appropriate representational space for those things, and then of course appropriate way of sort of feeding the material so that it gets represented. When I showed you the matrix here, it was mostly zeros because most documents don't. I mean, if you remember the number of documents, the number of words, and the length of document, most words don't appear in most documents. That matrix was mostly zeros. And so there's an opportunity to compress that matrix. And the standard method, the method it looked first was called latent semantic analysis, and it uses principal components or singular value decomposition. And then the one that I am more excited about is this random indexing, and so I hope to get the random indexing in the next half an hour. But let's first look at what the latent semantic. That's the old standard. That was in early 1990s, and so it became the challenge. I mean, you always have to have something that you want to do something better, and somehow something to beat. So latent semantic analysis also is being called latent semantic indexing. So if you go to Google search LSA, LSI they mean the same thing. And latent semantic indexing. So it's singular value decomposition. It uses principal components. But this kind of analysis has also been done with independent components. So there's several ways of doing math on that big matrix to compress it. And now yeah.
See, I thought it was interesting what you said that so most words that don't appear in most documents.
Yeah.
Is there a way in which you can think of words then as a kind of sparse representation?
Yes.
If you think of, if you thought of sort of like a network, we have one neuron per word, and if you looked at how this feature vector sort of lights up per document, then you see a small number of units firing per document.
Yes.
Right?
That's the picture of the matrix that I had there before. That I will improve that picture. That's what I call random indexing. In other words, that idea, but it is implemented in a way that somehow is more appealing to a neuro. I mean, if you think of how brains have to do things, because it's very hard for me to think anyway. The brain would have each cell. Each document would have its own neuron somehow. So that's what I'm getting away from. But let's go first through the standard method, and so what does singular value decomposition? What does it do? It takes the frequency matrix, words times document frequency matrix. It decomposes it into three matrices, A, B, and C. And words times R, that's the rank. The matrix F has a certain rank, meaning the total number of possible independent vectors in that. That's called the rank of the matrix. So the matrix can be exactly represented as the product of three vectors three matrices, an important thing is that the rank is smaller, or at most as large as the smaller of the two dimensions of the matrix. So that's the rank, and in the columns of the first matrix and the rows of the second matrix, they have unit length and they are orthogonal, and then this one is a diagonal matrix of principal components, or eigenvalues. So latent semantic analysis does a partial reconstruction of this matrix. I mean, this is a total. This is an equality. You can reconstruct it, and it takes a certain number of the dominant principal components and reconstructs a matrix of the same dimensions, where now only the in this case about 300 dominant principal components are used in reconstructing the frequencies, and now we have this matrix A. Now there's something wrong in here. Sorry. The rows of A have to be.
Where's the column?
This would be F. This would be F. Because these rows of A. No, columns. There may be something cockeyed here. I'm not sure if this is okay. And anyway, one of these matrices has 300-dimensional vectors, and they are improved semantic vectors. Reduce the dimensionality. The original row semantic vectors were 37,600 dimensional, and now we have only 300 dimensional semantic vectors. And when you do this, and then you do the synonym text, you actually improve the scores.
Now each column though is now a real number, right?
Now they have
It's now a floating point number.
They have become and the resulting, and they are no longer sparse. These 300-dimensional matrix vectors are no longer sparse. And when you go through this principal components, you end up with real vectors with real number components.
Have you actually done this on your data? And you looked
I have run this.
So when you typically do this kind of analysis, you can look at the amount of variance explained as you walk through the dimensions.
That's what the traditional people have done a lot of that. So you find a lot of that in literature.
So have you looked at how much of your variance is explained by the first 300 dimensions?
It turns out that if you increase beyond 300, your scores start going down. That there's actually
you're just modeling noise.
That there is actually there is some optimum number of the dominant principal components, and you should stop there, because if you have fewer than that or more than that, then you just in fewer than that you are not capturing all the data. If you're more than that, you're adding noise. But anyway, there was something wrong in that slide, and I just apologize. I didn't. What is true is that the new semantic vectors are only 300-dimensional. But where they exactly came from, that reconstruction, and now here is the competing method. How do you do semantic vectors with random indexing? Okay, here's what we have done so far, and I'll explain this. And then here's the opposite thing. I will explain what this means, and we have already gone through that, and then where we are heading with these. Okay, so we have this lots of text. We accumulate this matrix of frequencies, words times documents, and those were the dimensions in our example. Then we do the singular value decomposition, and then the reconstruction, and then we get words by now. That's the number of principal components. So we get there's still as many words as there are, but now instead of the vectors being this dimension, we have the dimensionality of the of how many principal components. So this is how latent semantic analysis is done. In random indexing, we start with the same text. We never collect this huge matrix, but we sort of collect a smaller matrix, and it still has a row for every word in the vocabulary, but instead of 37,000 some columns, each column, where each document has a column, we have gone into our beloved 10,000 that I promised to use in my examples. And so from this text we accumulate a sort of a quasi-frequency matrix. This was a frequency matrix F, and this is the sort of a corresponding quasi-frequency matrix G. And there's even a possibility, which I'm not going into in more detail this time. There's even a possibility of doing it in both dimensions, so that instead of having as many rows in the matrix as there are words, even though that's reduced to some matrix much smaller.
I'm sorry, how do you get your 10,000 columns?
I just chose a nice number that is big enough.
Yeah, but how do you fill the column?
Okay, that's the next step. Okay, the algorithm, random indexing algorithm. And it against the how do you accumulate stuff in this matrix G. The G was the corresponds to the frequency matrix. And I'm comparing it to how it was done previously. And the previously is up above and below. And in both cases we start with, okay, you start with the, you are at the beginning of a text, you start with the zero matrix. That's because you haven't accumulated any data yet. And now if you do the old standard method, for each document it had its own column in the frequency matrix, and we say that document activates that particular column. And then when we go through the text and find the word I, some word occurring in document J, we increment the cell in that. Okay, we are in the row I that corresponds to the word, and we increment the cell that corresponds to document J. So that's the way. That's actually exactly how when you go through the text word by word. That's what you do. You choose when you go to the beginning of a document, and okay, so you get your next J, next position in the next column, and then you go find what word. Okay, that word occurred, so you add there one, and that word occurred, you add there one, and so that's how the column for that particular documents get accumulated. It gets incremented as many times. Something in that column is incremented as many times as there are words in the document. As each word somehow gets entered into the matrix.
But how is that random? It seems like
Now, in random indexing, each document activates several columns. They are randomly chosen, and since there are 10,000 columns altogether in my new matrix, for each document, I choose randomly 10 positive columns and 10 negative columns. So now each document is represented by 20 randomly chosen columns. 10 of those will be designated positive, 10 negative. And so instead of a document affecting a single column, when you find a word in a document, instead of that word affecting something in single column, it affects something in every one of those 20 columns.
It's always the same ones.
But for that document, it's always the same columns. So when that word I occurs in the document J, you increment and decrement the cells in row I that document J activates. So you +1 positive columns, -1 negative columns. And so it is very much like accumulating the original frequency matrix, except that now you do 20 times as much work. In a matrix that's much smaller. You had a question?
Yeah, so are of your 10,000 columns, are 5,000 of them positive for all?
No. Most of them are zeros. Most columns don't get affected at all.
No, what I mean is...
10,000, okay, so 10,000, in a matrix there are 10,000 columns, yes, okay. And then?
No, my question is, can one positive column for one document be a negative column?
Yes.
For another?
Yes. Yeah. And it all happens by random, because each document is independently assigned its random positive and negative columns. Activates, the columns that document activates, they're chosen at random independently for each document. So I hope I can sort of give you the feeling how very similar these two ways of accumulating the original frequency matrix and this random index matrix that corresponds to it, how similar they are. And now this could probably be a sort of here. In this sense, I feel that this is sort of more like what could happen with neurons. Is that of course, how does this document get represented by these 20 random neurons, and how does that by something else? Well, but anyway, that they are not designated a single neuron or a single one, and that's but something that is derived randomly from it's a new document. You could, of course, in programs we get a new document, we just run a random number generator 20 times, and we get the next 20 columns, and you get a new document. Yeah.
Okay, this would be equivalent to pre-processing our documents, taking all of our documents and creating 10,000 positive documents where I take my original documents, I chew them up, I spit the words into these 10,000 positive documents and 10,000 negative documents using this random rule. And then I just process those.
No, document.
Only documents
Each document is both positive and negative.
Under the new rule.
Yeah.
I'm just trying to map in my mind the new rule to the old rule. And I'm saying that the new rule can be thought of as a pre-processing of the document into 10,000 positive documents, 10,000 negative documents, and then an application of the old rules.
Yeah. Okay. Yeah.
Would be another way of thinking about it.
It's very similar. Yeah. Good. Okay. Now these rows okay. Should I go back a couple of slides? Okay. So remember now. This still has a row for each word in the vocabulary. So it's each row, except that now the rows are much shorter. But by themselves, they already are valid semantic vectors. The dimensionality has been reduced, and they improve the test score compared to the original frequency matrix. That's the most sparse of all. The interesting thing here is that within those 10,000 columns that we have assigned, this time we did 37,000 some documents. But you can add documents. You just run your random number generator 20 more times, and you can add more documents and keep doing it. So that's one of the beauties of this method. You will not have to reallocate space. And then you can actually take this if you really love to do principal components, you can do it also in this matrix. And I think everything is linear, so I think you can do that. But from our results, it looks like it may not be necessary. Here are some results, comparable results. What we have done here is, here's random indexing, and here is the 10,000 that I have been using in my example. We did the experiment on this data. We did it with where the matrix G had 8,000 columns, 64,000 columns, very condensed matrix, and a number of plus ones and minus ones varied. In my example that I just presented, I had 10 here, 10 plus 10 positive columns, 10 negative columns. Okay, it turned out that 30 gave here. But anyway, it's of that order of magnitude. So you have this very large number of columns, and each document activates positively 10, negatively 10. In this case, positively 3, negatively 3. And here are the scores. Remember, 25 out of, no, there are 80 questions and 4. So 1/4 of 80. I guess that's 20. So 20 means that 20 correct means that you just were guessing. So here this got 31 correct out of 80, 35, 37, 44, 45, 44. So these random index vectors were produced. They, as we get larger here, they get 44 correct out of 80. Well, it doesn't very good. I mean, everyone of you here probably would do better than 44 question those. But still, some people get, I understand some people get universities with a score of 44. And here is here when you do the latent semantic analysis. Let me see. I have done it twice. Once latent semantic analysis, in other words, principal components based on the frequencies, absolute frequencies, and then based on the transform of the frequencies. I think it's log trans, which means that very large frequencies don't get such weight. And so the best scores using singular value using the principal components, they were in this column, and again 32 correct, 31, 40, 43, 45, and I think here my program refused to go to I don't know why it didn't go to 300s principal components, but in one case when I used the frequencies as such, it get all 300. But anyway, so we are getting comparable results with just this condensed matrix without any principal components. And I have the same here, but here I have to turn this sideways so that well, I don't know if this R is with the random indexing. Here is in one case I have the number of dimensions, in the other case number of principal components extracted, and it's just the same data that was in the table. So so number of correct 30, 35, 36, 41, 42, 40, 45, 44, and this is the. So well, that was just the same data. In other words, we get comparable results without doing any very fancy analysis. Now here I have two slides of mathematics, and I'm just going to say that, just for the title's sake, the random index vectors, each one of those documents has a random index vector that has 10 ones and 10 minus ones. Okay. The random index vectors for documents, they are approximately orthogonal. And that is, mathematicians will appreciate that. And the frequency matrix F that I originally showed you here, and the context matrix G that we generated later, they have approximately the same information, and I've just shown it here how it goes, but that's just easy to show that you can compute one from the other approximately from the one. Okay, so now a little bit of major contrast. Still, I've talked about them, but some sort of a summary. The random index is inherently incremental. And the dimensionality is relatively independent number of documents, and if you do the index in both directions, it's also a relatively independent number of words. So you can assign a certain amount of memory to start with, and keep adding vocabulary, adding documents, and your original memory assignment still holds. It avoids the heavy computation. And certainly incremental computation. I mean, if you add data and try to update the principal components, that would be quite a more computation. It's avoided, and some information is lost because it's only approximate. And then the random indexing, you can use other kinds of context, like neighboring words. In this case, the context was a document, each document. But also you can do the same thing. Each word in the vocabulary can be a context. So originally each word in the vocabulary gets a random index vector. And if it appears within a certain window, you go word by word, and then you have the window is the neighboring words. Instead of 300 words in a document, it's just like 4 neighbors in each direction. And you can use the random index in that way, and it works fine. It has been used. Then I think this could be extended into something like discovering grammar. But slightly, it's a good challenge, and it's something I'd like to see done sometime. And I mentioned two-way random indexing. You can in 10,000 by 10,000 matrix accommodate easily 1 million words and 1 million documents, and keep going. And this is I would say all work this is kind of scientific work I've done so far. This is the one that I would say is already ready for heavy-duty applications. And where would they be? They would probably not be in language research where I have demonstrated, but it would be something like analysis of sparsely connected matrices, networks, social networks, who is talking to whom on a telephone, spy networks, I don't know. Anywhere where new individuals come in, old go out, and it doesn't matter. You just throw the dice another 20 times, and you have again a new representation. And then I think in that kind of analysis, this is a very, very useful tool even today. I haven't gotten Google interested yet. Then I want to mention something that goes beyond what I here, and that is high-dimensional vectors can also be used as an idea of computing with them. they can be used to represent what in ordinary computers you have these data records that have divided into fields. You can put that kind of information into one of these high-dimensional vectors where each field actually occupies the entire 10,000 bits. So it's distributed representation. And you can do interesting mathematics with such vectors. You can also flatten sequences where you have your sequence is successive 10,000 bit vectors representing moments of time, for example. You can compress that into a single 10,000 bit vector, and then still recover individual components, approximately recover individual components. And so I see this additional things is leading into a sort of a new way of computing that uses instead of using 64-bit words or 32-bit words, it uses 10,000-bit words. I call it hyperdimensional computing. It's a little bit of hype. I think everybody's a little bit of hype. Neural connections. Well, the high dimensionality definitely comes from there, and the robustness that high dimensionality allows you. Then there's an interesting thing that I mean, we all sort of understand each other, yet, so we speak, we can communicate, we learn the same thing, yet no two brains are identical. So there has to be a system that somehow starts with unidentical stuff, it exposes the same material, produces somewhat equivalent systems. And in some sense, the example of random indexing is of that kind, is that I just use, for each of the documents, it just randomly chose 20 columns, and but when it's exposed to data, then the relations, I mean, you do the same experiment, one random number generated, another seed, you get similar results. And so this to me is somehow suggestive of how brains actually become equivalent computers so we can understand each other. And I use the term randomness, you heard the term path of least resistance. I use this randomness sort of the path of least assumptions. With very little assumptions you can produce interesting, useful systems. Here are some names and work that they have done that's sort of related to this. These kinds of high-dimensional representations. There's a holographic reduced representation. It's something that I believe is a sort of going to be very, very important, interesting, and the term context-dependent thinning. These are two Russian scientists. They have a very neat idea, but since being Russians, they couldn't think of a very racy term for it. But it's a very good idea. Well, yeah, shifter circuits, shifter circuits, Arathons. I believe you may have talked about Arathons circuits in here. And in my work, sparse distributed memory and a spatter code are some of these things. And here's sort of what I want to leave you with, and that is with the high-dimensional spaces. They have extraordinary properties, and I've only demonstrated some of them. The work that in the previous slide would talk about other things. And it looks like a new kind of computing can be based on them. This computing would be more brain-like than our present computers. And this is sort of a personal piece of faith or claim. If you want to understand brains, you need to make friends with high-dimensional spaces. That's just take it as an article of faith at this point. Here are some credits for the people who had done the LSA work, latent semantic analysis work. And if you want to read about that, this is sort of the best reference. And that's it. Well, thank you very much. I went 2 minutes over time. I'm sorry.
So for those who want to stick around and ask questions,
Yeah.
Pentti can stick around for a while. And but just before you go, just want to remind you, please turn in your evaluations in the back. Of course, evaluations, one for me, one for me. And